Gopi Boinpally, Senior Director of Power Products. Gopi joined Amkor in 2014 and is currently Senior Director of the Power Discretes product group. He has served in a variety of roles, including Technical Marketing and Business Development Manager for lead frame products, and various management positions within Amkor's mainstream business unit. Prior to joining Amkor, Gopi worked in marketing at Semiconductor and product engineering, business operations roles at Freescale Semiconductor.
It's loading.
Yep.
Yes.
So good morning, good afternoon, good evening to everyone joining from various parts of the world, and thank you for joining. So today I'll be discussing the market trends and some of the technology trends in power semiconductor packaging, and also discuss some of the challenges that we are facing and we will face as we look into the future. So first I'll start with the key market trends, technology trends that we're seeing, followed by some packaging challenges. And then we'll look into how power packaging might look in the future. And I'll conclude with the question and answer session and a brief summary. So first, if we look at some of the high-level technology trends in the power discrete world, as most of you may already be aware, power semiconductors market is at least 70 years old, with products supporting various applications in various market segments, right? From consumer to communications to industrial to automotive segments. So they are applied everywhere in all the segments. So over several decades, we've seen them evolving from traditional through-hole TO type packages to surface mount devices, going from gull-wing type of packages to leadless packages. And now with the shift in the overall power requirements, with the higher power requirements, we see surface mount device with dual cooling, both top side and bottom side cooling technologies, and low profile leadless alternatives, right? Like power CSP or embedded die solutions. We see those coming up. And on the silicon side, we have seen a steady improvement on the performance due to innovation in the silicon technologies, in the architectures, and they're successful in achieving device performance improvements with lower conduction losses, switching losses, and also while reducing the die size, overall form factor is reduced considerably, right? If you look at some of the interconnect technology side, we have seen innovation to achieve lower thermal resistance and overall lower package electrical resistance. So we've seen the market move from aluminum wire, aluminum ribbon to copper, gold wire, and now more towards copper clip technology to better address the thermal management within the package. Excuse me. So continuing to look on the substrate side, while silicon continues to dominate the market on the mid to lower voltage applications, the wide bandgap material devices like GaN and silicon carbide are already gaining popularity and are becoming more efficient solutions in some of these applications. These wide bandgap material operate, as you all very well know, at much higher voltages, frequencies, and temperatures compared to our conventional silicon devices. This higher temperature tolerance means that these devices can operate at much higher power levels under normal conditions. So here on the charts, you can see the market reports showing the projected growth of silicon carbide and GaN by application and technology. So these devices will be significant drivers for power semiconductor growth in the coming next decade. Like especially if you look at the application side, hybrid vehicles and electric vehicles are a major growth drivers, as you can see on the chart on the left side. And from a technology standpoint, it is the silicon carbide discrete power devices that are expected to take off in the coming years. So I'm going to talk a little bit more about these areas in the automotive and other segments in the following slides. But if you look at the silicon carbide device, silicon carbide based Schottky diodes have been in the market for more than a decade. Like silicon carbide based MOSFETs are appearing lately. And also on the power module side, we see silicon carbide power modules, like including the hybrid modules with diodes in there, IGBTs or MOSFETs all integrated. They're all becoming they're increasingly available now. So while GaN devices are not as widely used as silicon carbide in these applications, they are mainly sold into consumer market with fast charging applications where your power density and efficiency are critical. So now we started seeing their growth on the high power market applications, for example, data center side or power supply for base stations, or with the arrival of the 5G technology, we see more and more growth in that area. So if we look at the automotive driver, we have seen in the previous slide, some of the applications that are driving growth in these areas. It's predominantly driven by automotive sector and its electrification. So the growth of the number of battery electric vehicles or plug-in hybrid electric vehicles in the market, it's growing and it's driving growth in the overall power semiconductor business. So if you look at each of these subsystems within the electric vehicle, there are multiple power discretes supporting a range of functions at various voltage levels. Now, for example, if you look at the DC-DC converter subsystem, we can see silicon MOSFETs used for low voltage or medium voltage applications, whereas high voltage application is really handled by silicon carbide MOSFET. If you look in the other subsystems, that's the case. So if you look at inverters, both auxiliary and main inverters, that's the case where high voltage are handled by IGBTs or silicon carbide. When it comes to onboard charger systems, we see super junction MOSFETs or IGBTs being used. So what is also key here is to look at the amount of semiconductor content in these subsystems and the vehicle overall. It is all driven up by the power semiconductor content, and most of that value is going into inverter modules. So I'm going to talk about that in the next slide briefly. So as per the UBS estimates, you can see in the chart that semiconductor content value is significantly higher in an electric vehicle when compared to a ICE, the internal combustion engine powertrain. And so roughly 90% of the value is coming from the power semiconductors. And out of that, roughly around 50% of that is going into the inverter modules. So as I've shown in my previous slides, inverter modules are dominated by silicon carbide rectifiers or the IGBT modules. So roughly 80% of the silicon IGBT or the silicon carbide MOSFETs market will be taken up by the power modules in the coming decade. So the next driver for this power semi growth is the 48-volt ecosystem. There are several applications where 48-volt power architecture can provide a valuable and efficient solution. Three major areas that we have highlighted here are automotive, cloud computing, and industrial automation or robotics. Right? Today, automotive power designs are based on 12 volts bus, but as we move forward, 48-volt bus system will be adopted. As more and more functionalities get added due to your autonomous driving or all the infotainment solutions that are out there. So by adapting to this 48-volt bus, one can get higher power density and therefore smaller and more efficient motors. Right? So starter generators applications or battery management systems, all these can run on the 48-volt bus. On the cloud computing side, server needs to be powerful and efficient to take care of all the computational and networking activities. So peak power in those systems is also growing. And with such high power densities, a 48-volt bus would be a better solution than a 12 volts because now it lowers overall transmission losses. And now it also helps to reduce your conductor size. Another area where 48-volt power could be applied is industrial automation. Robots, delivery drones, and other devices that are battery operated would fall under this category. And with the adaptation of this 48-volt bus, their efficiency would improve. Some of these systems, like telecom systems today, it's already operating on the 48-volt system, but we still see a lot of potential on the automotive side and the industrial side to make the transition from a 12-volt to a 48-volt system. Right? Like car battery systems, data center servers are still operating at 12 volts. Industrial systems have moved over to 24, but then there are a lot of advantages in going to a 48. If you look at a quick trend on the power peak requirements on the computing side, if you look at the Intel data center chip roadmap, they are projecting the peak power to be above 1 kilowatt. That's a steep increase from where we are today. So with these high rack power densities, there is a need for higher power cores running on the 48-volt bus. So from a cloud computing architecture perspective, things are already shifting to two-stage conversion. Like one is using a transformer to convert to a lower AC voltage and then to a 48 volt and then to a load, or another one where there is a direct conversion from AC straight to 400 volt or to a 48 volts. So far, what we've seen now, how the market is growing in the next decade based on all these growth elements in different sectors. And with electrification, 48 volt ecosystem and high power requirements. So now I'm going to talk a little more about what are some of the challenges we come across in the packaging world. So for power packaging challenges, I would like to categorize these into, let's say, 5 power packaging areas. So power density, integration, reliability, environmental and human health, and manufacturability and competitiveness. So looking at these one by one, in the power density area, we see challenges due to die handling capabilities, like with the improvements in the performance due to all the silicon technology innovations, we now have to deal with much thinner die, 50 micron die or below. And there are other areas where there would be challenges, right? Others like materials, the interconnect technology, whether we use copper clip or aluminum wire, or with all the high power requirements, what is the wire capabilities that we can use? And on the thermal management side, with all the increasing power requirements, how do we manage the thermal portion of the package effectively? So we now need to come up with solutions to address this thermal management. For example, dual side cooling solutions, or you have to come up with mold compounds that have high thermal conductivity. So we'll take a look at specifics in the next couple of slides. But I also want to talk on the integration side. The whole industry is moving towards integrated solutions. That is, you have a controller die with FETs in there and passives all integrated into one package. On the high power module side, now the devices are integrated with a silicon carbide or a GaN die. And with all these components within one single package, now the challenge is to understand the interaction between these and the impact of these different components on the overall package, say from a CTE perspective or from a reliability standpoint. It's key to understand what's happening within the package. Now, looking at the reliability, obviously the requirements for reliability and performance are becoming more and more stringent, especially on the automotive side, with grade 0 qualifications, and most IDMs and tier ones are pushing for zero delamination and higher board level or system level performance, right? So qualifying to a Q101 spec is okay, but now we need to take it to the next level and look at a board level reliability, how we can achieve better performance at higher standards. Of course, we have to take care of the environmental and human health conditions also, which means we'd have to come up with lead-free materials and green molding compounds that would meet these new demands. And we'd have to introduce these things as we move forward. And all these things have to be addressed while maintaining manufacturability and cost competitiveness. We could come up with the best possible solution, but if it is not manufacturable, then we will not have a sustainable business. So it is very, very, very important to handle the manufacturability piece of it. So next, in the next slides, we are going to look at some of these challenges specifically from a material perspective and address some of the key areas like the lead-free die-attach solutions or high TG material and some of the zero DLAM activities that are ongoing. On the high lead solders, we all know that the most common die-attach material used today is the high lead solder, and we all know the harmful effects of that to human health and the environment. So therefore, there is a need for lead-free alternatives. At Amcor, there are several alternatives that are being evaluated, like silver sintering, hybrid sintering, where you have your silver sintering with added adhesives and other alternatives, but there is no acceptable alternatives yet. Like I mentioned earlier, its manufacturability is also very critical. Right? The challenges that we get in mass production, high volume, and of course the cost has restricted their overall success to some extent. Now, if you look at the chart that's shown there, we want to be operating in the area that's highlighted in blue, where you have the lowest electrical resistivity and the highest thermal conductivity from a packaging standpoint. Right? So we have some sintering material evaluations ongoing, but of course there will be a trade-off with cost and manufacturability in those. Next, if you look at the high TG EMC development, if you look at the typical lead frame devices, the operating range for a device there is in 100 to 120 degrees C. That's where the TG is in that range. And whereas for a BGA package, that would be roughly around 135 to 150. But in power semiconductors, that range is very wide. And depending on the application, it can be as high as 175 degrees and sometimes even higher. So with all the high power applications in the future and the growth that we are seeing, it is very critical to have a solution that can handle these high temperatures that these devices are going to achieve. Right? And that poses a challenge when combined with other reliability goals like the zero delamination, qualifying for automotive grade, qualifying it at higher board level requirements. Right? But then so far, we haven't qualified any compound that has a TG above 200. There are several EMCs in evaluations, of course, and there are efforts ongoing to find a reliable solution in that TG range. Next key material challenge we have is on meeting the automotive or high reliability requirements, especially on the delamination. Like most of these high reliability applications require zero delamination, and one of the solutions to eliminate this delamination in the package is to use some kind of adhesion promoters on the lead frame. And some of the key interfaces, if you look with delam concerns, are your EMC to lead frame, EMC to solder to aluminum pads on the die, and on the plated surfaces on the lead frame. So most challenging one of these is from EMC to solder. That's where we see most of the issues on the delamination side, right? And that's where we spend most of our resources addressing that issue. So I believe some of the IDMs are already working on their own solutions to address this problem, but there is no standard industry-wide known solution. Of course, there will be other challenges as we get into newer generation of devices from a design standpoint, from a material standpoint, from reliability standpoint. And as one of the pioneers in the power semiconductor packaging, we are certainly looking into some of these key areas to address these widely known problems. So now with that, we have so far looked at some of the trends in the market and technology and some packaging challenges. Now it's time to look at the future and see how the power packaging is evolving. The future of power packaging, it is directly tied to the growth in these markets that I have already discussed, like the automotive, the 48-volt ecosystem, where we have seen growth in cloud computing, industrial automation. So to be a part of these growth markets, we need to have some of these key innovation milestones, such as having a modular package with different package components integrated, packages supporting high-end applications, high-power applications using silicon carbide and GaN. We have to come up with innovative solutions for new materials and designs to address high power and thermal management requirement. And ultimately, the whole goal is to improve the product performance improve the power density, improve the product performance per watt, right? So along with these areas, we need to have further innovation for new materials to provide better mechanical stability and robustness, as well as we have to take care of the bonding mechanisms, how they can be improved to better withstand extended power and temperature cycling. So there's a whole lot of innovation in that area that's still required. And one of the key areas in the future that we see will be also modular packaging. So power modules where all the designs are trending towards a similar architecture. Now at a system level, it's more integration design with lead frame or laminate combined into one package. You have lead frame, laminate, or a ceramic substrate. It has molded interface between these substrates, and passive components or other package discretes are being integrated into that package. Now at a module level, with all the heat generated due to power switching, dual side cooling is becoming a popular solution also. At a device level, IGBT, silicon carbide, IGBTs, they are integrated into these modules as new materials. At Amkor, we are able to address most of these challenges that we have discussed through a full suite of packaging solutions. On the technology side, we have devices running with silicon carbide and GaN die. We are supporting those devices. We're working on lead-free alternatives for die-attached material. We're working on the IGBT modules, and we're also coming up with newer low inductance power CSP packaging. And on the reliability side, we are definitely working on addressing the zero delamination concerns, and then some of the system level requirements. We have recently integrated all our Japan factories into Amkor, and which has now we can say that Amkor has 2 dedicated sites supporting power packaging and also capable of supporting IGBT modules. Now, we also have a dedicated team. We are looking at the next generation of packaging technology with our power CSP device and more advanced power QFN modules. So in summary, power semiconductor market is advancing and it's growing into newer technologies driven by changing macro level trends. You can clearly see electrification is the driver combined with computing and 5G growth. From a technology standpoint, it's very critical to reach some of these innovation milestones, like the modular packaging packages supporting high-end applications, coming up with new materials and designs to address these requirements on the thermal side, and ultimately improve the product performance, right? But last but not least, it is very critical to understand the trend and to understand which technologies to invest in. This is very critical because timing is also very important to the overall corporate success and overall industry success. So to conclude, we at Amkor definitely have our hands full trying to meet the power semiconductor packaging needs. Finally, I'd like to close this by saying that you can explore more about Amkor power packaging capabilities at amkor.com/power, or you can contact me and I'd be more than happy to discuss with you. And thank you for giving me this wonderful opportunity. Thank you. Open to any questions.
Yeah, thanks, Gopi. So that's a good point. If you have any questions, feel free to unmute and ask, or you can again enter it into the chat box and I will ask it. So to get the ball rolling again, I have a question for Amkor regarding the packaging. You were mentioning you're going to go into modules. Are you looking to do transfer molded modules, kind of targeting, the traction market, or are you looking to do more gel fill modules going for the industrial?
So right now, what we have experienced is doing transfer mold modules with lead frame and other ceramic substrate or any other substrate integrated into it. But we are working with different partners to see where the industry is going. If gel fill modules is what is driving the growth, then we are open to looking into that as well.
Okay, thank you. So we've got a couple of questions coming in now. So one from Jan Vardaman again. Have you looked at the copper sintered materials for die attach? Good question.
Yes, we have definitely looked at that. We have looked at it from a different types, like the pressure versus non-pressure. I cannot give more details on that, but we are definitely looking into that materials to see how they perform at different conditions.
Okay, thank you. A question from Paolo Cassetti is, any experience on highly conductive film die attach material? Another good question.
On the die attach material, we do have some production running on using the die attach film. It's a but when it comes to high conductive die-attached film, we have some work going on. That is not what we are predominantly using in our manufacturing today, but there's a lot of work to be done in that area to get that into production.
Okay. The next one's from Andy Kabatz. Thanks, Gopi. Does Amcor offer any low-cost entry options to address the high NRE costs? And the example is tooling for a copper clip is quite high. Maybe using a laser cut lead frame as an example.
Yeah, so when it comes to NREs on these power packages, yes, I agree, they are on the higher side. And that's because of all the volume that we get using the stamp lead frames or stamped copper clips. But if NRE is the primary factor stopping in doing business with us, Amcor is always willing to work with the customers to see how we can address that.
Okay, and then I think the last one from Tony Tao is which markets segments do you see growth in power CSP or QFNs?
So on the power CSP side, the target market there is more on the automotive side. We have seen interest from the customers to put those in the automotive environment, and on the power QFN side, we have growth seen in the networking side.
Okay, I think we've got time for one more. So Ryan Sharma, he's asking, is there any advantage in using sintered copper versus sinter tin for DA? Sorry, sintered silver.
Sintered silver?
Yeah.
There are definitely, if you look at the overall operating area where you see your sinter silver versus hybrid sintering versus your sintered copper. In the chart that I have shown, basically we have looked at sintered copper. It falls into the top portion, but it is cost prohibitive. So yes, it does have some advantages, but can we put that in manufacturing? We are not there yet.
Okay, and then one question, oh, there we go. I think we're coming close to time, but how do you achieve zero delamination?
That's a good question. That's what we're trying to figure out, is how do we achieve zero delamination? We have a lot of activities going on. We are trying different mold compounds, and obviously working with the suppliers to see what kind of adhesion promoters we can use to make sure. Obviously, there are some challenges there too, because if you're trying to solve that, it also impacts the manufacturing side. So now you'd have to clean, let's say, your mold chase more frequently. So that would impact your cost directly. So there's no short answer for that. Yes, we are still working on getting a zero delam solution.
Okay, question just from me is that, you see silicon carbide and maybe some GaN in standard TO packages like a TO220, TO247. Going forward, do you think these packages for silicon carbide and GaN are going to continue? You've got these big lead inductance packages. Do you think the standards are going to change and you're going to have these new type of TO packages, or some type of a QFN or PQFN style dual cool packages going to replace TO247s in the future?
Yeah, we already see that trend. Your through hole packages, the TO220s, TO247s, they're already being replaced with newer generation packages. If they can work with a leadless package or SMD with gull wings, they're being replaced. If you take a package like a TO252 or a TO263, like the D square pack, those are already being replaced with leadless packages like TOLL package, or an LF pack is something that can substitute that. So yes, we are definitely seeing that trend, moving from through hole type packages to more surface mount packages, and going into future, we see more integration in them.
Okay, then I think that hits it just on time. Thank you. I think there's no more questions. So thanks, Gopi. Appreciate that. It was very insightful. Very interesting to see, because packaging is always a big issue with thermal management and strain inductances. So thank you very much. Thank you.